Hello everyone. I'm Ummi Hani. I belong to Department of CSE Artificial Intelligence. So, today I am back with the new topic to present over here. Today the topic here is let me start with it. Firstly, I welcome all of you to my YouTube channel. The subject to discuss here is theory of computation. The topic here is closure properties of context-free language. So, let us know what is closure property in context-free language. Introduction to context-free language. Context-free languages are a class of languages defined by context-free grammars. They are essential in study of formal languages and automata theory. Understanding closure properties helps in analyzing the capabilities of context-free languages. So we also have context-free grammars like let me tell you CFG. CFG is nothing but context-free grammars wherein G is equals to VTPS. V is a finite set of variables wherein S belongs to V. S is the start symbol. T is a set of terminals and T intersection V which is equal to phi. And P here is finite set of productions or rewriting rules. Each production is of the form. So let us move forward. Definition of closure properties. Closure properties refers to the ability of a class of languages to remain within the same class after certain operations. For context-free languages, these operations include union, concatenation, and clean star. Closure properties help determine the limits and capabilities of context-free languages. Union of context-free languages. The union of two context-free languages is also context-free. This is demonstrated by creating a new grammar that combines the productions of both the grammars. An example is combining languages L1 and L2 with a new start symbol leading to either L1 or L2. Concatenation of the context-free languages. So, context-free languages, here what is the role of concatenation? The concatenation of two context-free languages is context-free. This involves performing a new language by concatenating strings from two context-free languages. A grammar can be constructed by adding productions that facilitates this operation or this concatenation. Clean star of context-free language. The clean star of a context-free language is also a context-free language, we can say. This operation allows us for the repetition of strings any number of times, including even 0. The corresponding grammar can be adapted to produce strings that reflect this operation. As you can look into the examples mentioned in the picture. Intersection with regular languages. The intersection of a context-free language and a regular language is a context-free language as well. This is due to the closure properties of regular languages, which can be represented with finite automata. The intersection can be simulated using a push-down automaton for the CFL combined with a finite automaton. As you can look into the picture over there, like how it goes on, recursively enumerable, context-sensitive, context-free, and regular language. Intersection of context-free languages. The intersection of two context-free languages is not necessarily context-free. This is an important distinction as it limits the operations that can be performed on context-free languages. A counter-example can be constructed using specific CFLs that are known to produce non-CFLs results upon intersection. Complement of context-free languages. Context-free languages, here what are they actually? The complement of context-free languages is not guaranteed to be a context-free language. This lack of closure under complementation is a significant limitation of context-free languages. The proof often involves demonstrating that certain languages cannot be generated by any context-free grammar. Closure under homomorphism. Context-free languages are closed under homomorphism operations. A homomorphism maps symbols from one alphabet to strings over another alphabet. This allows for the transformation of strings while preserving the context-free nature of the language. Context-free languages under homomorphism. For example, if L is a regular language and H is a homomorphism on its alphabet, then H of L is equals to H of W, or W is in L is also a regular language. For the proof, let E be a regular expression for L. Apply H to each symbol in E. Language of resulting RE, that is regular expression, is H of L. So now let us study about closure under inverse homomorphism. Context-free languages are also closed under inverse morphism. This operation applies a homomorphism in reverse, mapping strings back to their original forms. It preserves the context-free property, allowing for the generation of new strings. For example, inverse homomorphism, let H of 0 is equals to AB and H of 1 is equals to epsilon. Let L is equals to so and so wordings, like so and so languages as mentioned over there, AB, AB, comma, BA, BA. H inverse of L is nothing but the language with 2 zeros and any number of ones. Yes, so L of 1 star 0 1 star 0 1 star. What it tells actually here is no string maps to BA, BA, and any string with exactly 2 zeros maps to AB, AB. So this is how it goes. Closure under substitution. Context-free languages are closed under substitution. This means that replacing symbols in a context-free language with other CFLs will yield a CFL. The resulting language is still context-free as the structure of the original grammar can be maintained. Non-closure under intersection and complementation. The non-closure properties of context-free languages highlight their limitations. Understanding these boundaries is crucial when designing algorithms for parsing and language recognition. This knowledge informs the choice of grammatical frameworks in computational linguistics. As you can look into the picture mentioned over there, closure under intersection, how it goes. Now let me talk about the applications of closure properties. Closure properties have practical implications in compiler design and programming language theory. They help in optimizing parsing strategies and grammar transformations. Understanding these properties aids in the development of efficient algorithms for language processing. So the implications over here are, let me first define what is implication here. The term implications has two interlined meanings. Firstly, implications are the possible outcomes or the consequences that can arise from a particular action or a statement. Secondly, they are the possible hidden meanings in a statement. In both contexts, they refer to unspoken or indirect information. Let me talk about a few examples and implications. Implied speech. What is implied speech? For example, if a person says it is sure or he is sure that it is represented in a unique way to paint a room, they might be implying that they find the paint choice not their taste. Implications of economic policies. Yes, so implementing higher tariffs on imports can protect domestic industries but might not always lead to trade wars. Yes, so this is how the implications as an application works in the closure properties. Let me conclude the session by concluding closure properties are fundamentals in understanding the limitations and capabilities of context-free languages. They play a vital role in both theoretical and computer science and practical applications. A solid grasp of these properties is essential for anyone working with formal languages and automata. So this is how it goes when it comes to a context-free language. So by ending the session, thank you. I would like all of you to tell that please kindly like my video, subscribe and share it. Thank you.